Hi, my name is Rahul Chauhan and I'll be presenting my final project on AlphaGo Zero implementation using reinforcement learning for the class Machine Learning under Dr. Jihu. What's the motivation behind implementing AlphaGo Zero? Google's DeepMind has shaken the world of reinforcement learning and the game Go with its creation of AlphaGo, which is later called AlphaGo Zero. It is the first computer program to beat a human professional Go player, Lee Sedol, by 4 games to 1 and many other top-ranked players by the version of AlphaGo Zero. In the image you can see on the left hand, the guy is playing the moves that AlphaGo program tells, and on the right, he is the Lee Sedol, the world's champion. The game of Go is a difficult environment because of its very large branching factor at every move, which makes classical techniques such as heuristic search unrealistic. I'll be presenting my work on reproducing the paper as closely as I could. Before diving into the implementation of AlphaGo Zero, let's just see what exactly reinforcement learning means. Reinforcement learning is a type of machine learning in which a computer program learns to perform a task through repeated trial and error interactions with a dynamic environment. The learning approach enables the computer to make a series of decisions that maximize a reward metric for a task without intervention or without being explicitly programmed to achieve a task. To better understand the reinforcement learning, let's just look around a real-world scenario. So, the goal of the reinforcement learning in this case is to train the dog, which is agent, to complete a task within an environment, which includes the surrounding of the dog as well as the trainer. So the trainer here is the environment, the girl who will be throwing stick to a dog. First, the trainer issues a command or a cue which the dog observes. Now that is the observation. The dog then responds by taking an action. If the action is close to the desired behavior, the trainer will likely to provide a reward such as a food treat, a toy or something like that. Otherwise, there will be no reward or a negative reward. At the beginning of the training, the dog will likely to take some random actions like rolling over when the command given is to sit, as it is trying to associate specific observations with actions and rewards. This association, or we can say mapping between observations and action, is called policy in terms of reinforcement learning. From the dog's perspective, the ideal case would be one in which it would respond correctly to every command so that it gets as many treats as possible. So the whole meaning of reinforcement learning training is to tune the dog's policy so that it learns the desired behaviors that will maximize some reward. After training is complete, the dog should be able to observe the owner and take appropriate action. For example, sitting when commanded to sit by using the internal policy it has developed. So over the time, the trainer or the environment let the dog, which is agent, to learn some of the policies by recurring moves. By this point, treats are welcome but shouldn't be necessary. This means that it is not necessary that a treat will be given to the agent or a program will reward something to the move. It depends on how effective the move is. Reinforcement learning algorithms. So this figure shows few of the algorithms under reinforcement learning. I won't be explaining them, but it's worth mentioning that few of the most important algorithms rely on deep neural network policies. So the biggest advantage of neural networks is that they can encode really complex behaviors, which open up the use of reinforcement learning in applications that are otherwise intraceable or very challenging to tackle with alternative methods or some of the traditional methods. A trained deep neural network policy is often treated as a black box, meaning that the internal structure of the network is so complex, often consisting of million parameters, that it is impossible to understand, explain, or evaluate the decision of the network. This makes it hard to establish formal performance guarantees with neural network policies. From the previous example of the dog, even if you train your pet, there are still be occasions when your commands will go unnoticed. Now, another thing to keep in mind is that reinforcement learning is sample efficient. This means that in general, a lot of training is required in order to reach a proper performance. For an example, AlphaGo. We know it's the first computer program to defeat the world champion of the game of Go. It was trained non-stop for the period of few days by playing millions of games and accumulating thousands of the years of human knowledge. Even for a relatively simple application, training can take anywhere from minutes to hours to days. For me, it took around weeks to train my model. Now it's time to talk about the implementation of AlphaGo Zero. We'll start with the pipeline overview. AlphaGo Zero pipeline is divided into three main components, each in a different process that runs the code asynchronously. The first component is the self-play. It is responsible for the data generation. The very next component is the training, where freshly generated data by the self-play component is used to improve the current best networks. And the final one is evaluation, which decides whether the trained agent is better than the agent that is currently used to generate the data. Now, this last part is crucial since data generated should always come from the best available networks in order to generate quality moves much quicker than the self-play process. To understand it better, I'll be explaining every part of the code. Before diving into individual components, I would like to tell you about some prerequisite knowledge about the project. The project is implemented for Go game on board of size 13x13 with the Chinese set of rules and the Komi value of 7.5. This project is implemented for 2017 paper by Google DeepMind. Also, I have used Monte Carlo tree search with a single neural network that gives policy and value predictions with a self-play based adversary strategy to learn how to play by itself. Let's talk about the components in details. So the very first one is the agent. The agent is composed of three neural networks that work together: a feature extractor, a policy network, and a value network. This is also why AlphaGo Zero is sometimes called the two-headed beast, a body which is a feature extractor and the two heads, policy and value. The feature extractor model creates its own representation of the both state. The policy model outputs a probability distribution over all the possible moves, and the value model predicts a scalar value of range this given -1 to 1 to represent which player is more likely to win given the current state of the board. Both the policy and value model use the output of the feature extractor as the input. Now, the next one is the policy head. The policy network model is a simple convolutional layer of 1-to-1 convolution with a batch normalization layer and a fully connected layer that outputs the probability distribution over the entire board plus one extra move for pass or assign. So this is the extra move that is like if a user or player wants to pass or end the game. The next one is the value head. The value network model is a bit more sophisticated. It also has the couple of convolutional batch normalization, ReLU, and then a finally fully connected layer. Another fully connected layer is added on the top of the DAG. Finally, a hyperbolic tangent is applied to create a scalar of range -1 to 1 that represents how likely the player is to win given the current state of the game. We'll talk about the policy head and the value head in more detail in further slides. Another major component of AlphaGo Zero is the asynchronous Monte Carlo tree search. This tree search algorithm is useful because it enables the network to think ahead and choose the best moves thanks to the simulation that it has made without even exploring every node at every step. Since Go is a perfect information game without a perfect simulator, it is possible to simulate a rollout of the environment and plan the response of the opponent far ahead. So it's similar to what we humans do. Now, the nodes of the Monte Carlo tree search. Each node in the tree represents a board state and stores of the different statistics. The number of times the node has been visited is given by n. The total number of action values denoted by w. The prior probability of reaching node is given by p. The mean action value is given by q, which is equal to something like w by n. Now, this is what it looks like, the node defined in the code. Before talking about the policy and value network, I have used the ParchPy simulator to model the dynamics of the environment. The agent can carry out multiple simulations starting from the same state in the copy of the simulator to propagate the value up of the search path. This way, the more number of simulations of Monte Carlo tree search, and it makes better choices for different moves. Now, we'll talk about the policy and the value network. I've tried several architecture tweaks like changing in the order of layers, number of convolutions, type of pooling, use of regularizers like dropout or batch normalization. I have reported in the code base and in the PDF report the best architecture which gave me the best accuracy. To give a brief, this network combines the role of policy and the value network into a single architecture. It consists of the convolutional layer followed by 10 residue of 2D convolutional layers with batch norm and ReLU activation. The output of this fed to two heads, the policy head and the value head. We have already discussed about it in the previous slides. A distribution over legal actions, the value of the head consists of a convolutional layer is followed by two fully connected convolutional layer and TANA function. This shows an overview of the architecture which is defined in the code base. Now we'll talk about the loss function that I have used in the code. The loss function used for optimization consists of summation of the value loss and the policy loss. So the value loss, a mean square error loss between value predicted by the network and the reward at the end of the episode. For the policy loss, a cross entropy loss between the policy predicted by the network that is given by Monte Carlo tree search. Stochastic gradient descent with momentum is used for training. L2 regularization was used for all the parameters of the network. Next, these are the parameters that are defined in the config.py. So these are the parameters that gave me the best model for the reinforcement learning for AlphaGo Zero. So these are the parameters which can be changed easily in the code base. Now we'll see the working of the code. It's not exactly the working. I am training the data again to see that what good results it can give. I've already taken the observation from the tensor board, but I still have few of the files that I'm still running on Dr. Ho server. I'll show you these before the final observations. Just now we saw the training part, so I'm training the model again to see if I can get more accuracy. I've already got the accuracy and I'll be placing the same model in the code base. Now it's time to see some of the observations that I've got. So I'll be showing in total 6 graphs here. So the following of the graph shows the variation of loss as one episode progresses with increasing number of the episodes. It can be noticed that although the total value of the loss fluctuates and does not continuously decrease, the overall loss and the total policy loss continuously decrease. The fluctuations in total loss are not of the big concern since the scalar value of loss itself is very small. So it is of the power 10 e to the power minus 3, which is comparatively really less.